All right, so I think this is recording. Let's take a look at these three equations. They are relations, um, and we want to find the domain and the range of each relation. So for the domain is always by default the set of all real numbers, but then you have to exclude any values of x that cause division by 0 and any values of x that cause us to take the square root or even root of a negative number. So let's jump in and take a look here at number 15. This is the cube root, and this is an odd root. It's okay to take the cube root, odd roots of negative numbers. So there is no variable in the denominator. There is no variable underneath an even root. So the domain for number 15 is all real numbers. And we're going to see that the range is also going to be all real numbers because unlike even roots, these principal roots are always 0 or positive. But with these cube roots, the output can be negative, it can be 0, and it can be positive. So the graph is going to illustrate that the range of this function is also all real numbers. Let's take a look at number 6. We'll graph this in just a minute. We'll verify that on a graph in just a minute. Again, you're going to be saying this over and over. The domain is the set of all real numbers, excluding any values of x that cause division by 0. I don't have any variables in my denominator. I don't have to worry about division by 0. You also have to exclude any values that would cause you to take the square root or any even root of a negative number. Well, we don't have any square roots in this equation, so we don't have to worry about that. So the domain is all real numbers. Now, I know from previous experience that the graph of this is a parabola that opens upward because that's 1x squared. Okay, so I know that this point that's referred to as the vertex is the minimum point of this graph. All of the other points that are on this graph all have y coordinates that are bigger than the y coordinate at the vertex. So if you recall, you can find the x-coordinate of the vertex by just remembering the formula negative b over 2a. The opposite of negative 6 is positive 6. 2 times 1 is 2. So the x-coordinate of the vertex is 3. But I'm wanting the y-coordinates because I'm trying to use this graph to help me to determine the range. So the y value, the corresponding y value, well, I simply plug in this value of x equals 3 into the equation. So I have 3 squared minus 6 times 3 plus 1. And what do I have here? Well, this is 9 minus 18, which is a negative 9. And negative 9 plus 1 is a negative 8. So I claim that the range of this function, that we do have one point that has a y-coordinate of negative 8, and all of the other points are above that, going all the way up to positive infinity. So I believe our graph is going to illustrate that the range of this function is from negative 8 to positive infinity. All right, let's take a look here at number 17. It's a little bit more of a challenge. For the domain, we start out the same way each and every time. The domain is always the set of all real numbers, excluding any values that cause division by 0, and also excluding any values that would cause us to take the square root of a negative number. All right, so I'm concerned that I have a variable in the denominator. I don't have any radicals, so I don't have to worry about taking the square root of a negative number. But I am afraid that there might be values of x that would cause this expression to equal 0. Well, I need to factor this. And with the leading coefficient of 1, it's not that bad to factor. Two numbers, when multiplied together, give me a negative 14, but when added, give me a negative 5 or negative 7 and positive 2. So x equals 7 or x equals negative 2. Those two values I have to exclude from my domain. I can't allow x to equal 7. I can't allow x to equal negative 2, because if I did, my expression up here would be undefined. So let's put this on a real number line. Negative 2 is to the left of positive 7. And I'm excluding these two values from the domain, so those are going to be hollow dots. But those are the only two values I'm excluding from the domain. Those are the only two values that satisfy this equation. They're the only two values that make this denominator 0. All of these other values will not. You will get a corresponding y value if you plug in any of these for x. So our domain is the set of all real numbers from negative infinity up to negative 2, excluding negative 2, up to 7, excluding 7, all the way up to positive infinity. All right, so the range on this is much more challenging. Even with the graph, it's going to be pretty challenging to figure this out. So if I try to think about it without the graph, what am I expecting when I think about the range? Well, the one thing I know for certain is with this numerator being negative 1, that this fraction will never equal 0. I know that 0 is not in the range. But to exclude other values, I'm not sure, and I'm going to have to go to the graph. So let's back up and let's take a look at the graphs of 15, 16, and 17. And for 15 and 16, confirm our answers for the range. And for number 17, help us finish our answer for the range. All right, so I've already keyed this in. And for number 15, we had the cube root of 4x minus 2. That domain was the set of all real numbers, and I believe the range is the set of all real numbers. And this graph is illustrating that because it does have an x-intercept, so there is a y-coordinate of 0. And for any values here, I can plug in any x that I want and make it as big as I want, and I'm going to get a corresponding y value. And I can make x as small as I want, and I'm going to get a corresponding y value. If you don't believe me, you can play with this table, and you can't find any value of x that every value of x that you key in is going to produce exactly one y value. So that's how I know that the domain is all real numbers, because as I move to the left here, it's going all the way out to negative infinity. And as I come in and move to the right through the graph, there's no holes, there's no jumps in the graph, all the way until I get to the right end there. And then it's going all the way out to positive infinity. So the range is clearly all real numbers. Now, what about this parabola? We know that the graph of this guy is going to be a parabola that opens upward. And we use the negative negative b over 2a to determine that the vertex was 3 comma negative 8. So if you take your mouse and hover it over that vertex, you can see that the coordinates of that point shows up, and it's 3 comma negative 8. So as far as the domain goes, left and right movement, as we come in from the left on the graph and we trace out this graph, there's no holes, there's no jumps. And as you move to the right, you continue moving to the right. You have to go up at the same time, but that's the range. See, the one thing that's difficult about the graph is the graph provides you two pieces of information at the same time. It provides you information about left and right, about the x-coordinate, but also about up and down, the y-coordinate. And you have to train yourself to simply think in terms of movements left and right for the domain and up and down for the range. So for the domain, it's a set of all real numbers. And for the range, we can see that there is no point on this graph that is below the vertex, and that y-coordinate is negative 8. All these other y-coordinates are bigger than negative 8. Hold your mouse down at any point and look at the y-coordinate as you move through this graph, and I guarantee you that that y value is going to be bigger than negative 8. All right, so that confirms our answer for number 16, that the range was negative 8 to infinity. Now for this number 17, for this harder type of problem. What does the graph of this thing look like? Well, here it is. So we knew that we threw values out of the domain. So we know that when x was equal to negative 2 or positive 7, if x is equal to negative 2, my graph is never going to touch that black line. You may have to zoom in closer and closer to see that it's getting closer but never touching it. And it's also never going to touch this positive 7. So let's graph x equals 7. So there we can see that those values are thrown out of the domain. Our graph is never going to have an x, there's no x coordinate of 7 on this graph because there's no corresponding y value. The graph never touches that line. And on this line, the one thing that's true about this line is x is equal to 7 everywhere on this line. Since the graph never touches it, x is never 7 in the graph of this function. So what do we notice about the range? Well, from below, we can see that it is going straight down, that it's going towards negative infinity. As I come up, I've already determined, I already knew that since the numerator could never be 0, it's always constant, that 0 was not in my range. So that bottom portion of the graph is telling me that my range is from negative infinity up to 0. But then I see that there's a portion of this graph that's above the x-axis, and I also see that right here there looks to be a gap, to where it's not getting infinitely many close to the x-axis. Out here, this is getting closer and closer and closer and closer and never touching it. But in the middle here, it's not getting closer and well, it is getting closer, but at some point, it's almost parabolic. It's almost like that right here is kind of a vertex. So you could use calculus methods later on. They will show you calculus methods to determine that exact value. Knowing that there is a minimum value, I just played around with finding the coordinates of the vertex of this y equals x squared minus 5x minus 14, and then I took the inverse. So what I did to just play around, to give me something to play with on the graph and something for you to think about. I found the x-coordinate, if I treated this denominator like a parabola, and I took the opposite of b over 2a, and the opposite of -5 is +5, and 2 times 1 is 2. And if I plugged in that 5 halves into here, 5 halves squared minus 5 times 5 halves minus 14. What did I get? Well, the first term is 25 over 4. The second term is 25 over 2, so if I multiply it by 2 over 2, I'll have 50 over 4. And then if I multiply 14 by 4 over 4, I have 56 over 4. And if I add these together, I have -81 over 4. And if I take the reciprocal of that, I have -4 over 81. But remember, there was a negative sign up in that numerator. So I was curious as to, well, if I plug in 4 over 81 into the table, if I let the graphing calculator, tell me what the y-coordinate is for that. So I came in and converted this to a table, and then looked at 84 over 81, and let's delete these other points. Okay, now wait a minute. Maybe this isn't as illustrative as I thought. Where's my 4 over 81? Is that? Why do I have 81 here? Because I added -25 plus 25 plus 56. Is that what I did? Yeah. So 81 is right. So 4 over 81. So oh, that's a y-coordinate. What if I come back and plug in 5 halves? Yeah, there we go. Okay, and look, that 4 over 81 is, do that on a calculator, and 4 divided by 81 is like 0.04. This decimal number is 4 over 81. So that's the rate. That 4 over 81 is the minimum y value when I'm in between this x equals -2 and x equals 7. So this is a little bit above. I would not ask you a problem like this on a quiz or on a test or anything. But for homework and stuff, homework is a time to explore, to think about things. So it's okay for a homework assignment. Just don't leave it blank. Just try to make some attempt to get the coordinate of that point. So I claim then the coordinate of that point, the y-coordinate there, when x is 5 halves, that we have 4 over 81. Now it's at that point it is touching, the graph is going through that point. So I have a bracket here at 4 over 81, comma, infinity. So this guy was definitely a very challenging problem, but not impossible. I'm sure that some people may have figured it out or came close to figuring it out. And now that they've seen this, and if they practice and did a few more, you'd be able to do it. So anyway, I hope this helps, and I'll talk to you later. Bye.